Hello, everyone, and welcome to another wonderful day of chemistry. So today we're going to be looking at how we can use reaction rates to look at an equilibrium reaction. So one of the first things we can do is try and look at the simplest reaction, the equilibrium reaction we can think of. A goes to B, goes back to A. You let the system sit long enough and it will eventually reach equilibrium. But what does it really mean when I look at equilibrium? Well, to understand this, we can go ahead and take a look at the two rates of this reaction. First, we've got a forward rate, and then we've got a reverse rate. Now, we're going to assume that both of these reactions are going to behave first order. Well, in that case, the forward reaction is just going to be our forward reaction rate constant, which we're going to call K1, and times the concentration of the reactant, in this case, A. However, for the second reaction, now suddenly B is going to be my reactant, and it's going to be going in the reverse direction. So we're still going to depend upon the first order concentration of B, but now we have this new rate constant. We're going to denote this as K-1 to indicate that it's the rate constant for the reverse action, a reaction, which is what this negative sign shows, of the first reaction. So K1 means we're going forward. K-1 means we're going in reverse. Now, once we get a system at equilibrium, what does this really mean? Well, to be at equilibrium means the system has to be steady or constant. And this is going to happen when we have equal amounts of the forward reaction as the reverse reaction. Thus, as I let the system sit, it doesn't end up moving in any net direction. It just sits still by constantly moving in place. So for an equilibrium reaction, we can set these two rates equal to each other. The forward rate is equal to the reverse rate. And this gives us a lot of power because we can then essentially use this to determine the relationship in between our two concentrations and their rate constants. We can get a little bit more insight if we go ahead and take a look at the equilibrium constant for this reaction. So the equilibrium constant for this reaction is, again, products over reactants. However, if we write this in rate form, we know that these forward and reverse rates are equal to each other. So we can then rearrange this set of rates to give us the concentration of products B over reactants. We can do that by dividing both sides by the concentration of A and both sides by the rate constant for the reverse reaction. And suddenly what we see is that our equilibrium constant is going to be equal to the rate of the forward reaction over the rate of the reverse reaction, or the rate constants, which actually makes a lot of sense. If I have a very favorable forward reaction, it means I'm going to have a lot of products and a large equilibrium constant. If I have a very favorable reverse reaction, meaning that as soon as I form B, I quickly make my reactant back again, then I'd have a large reverse rate constant, a low concentration of B, high concentration of my reactant, and a low equilibrium constant. And this really shows how all of this is synonymous. And it really does show that when we are at equilibrium is when we have equal forward and reverse rates. And it is worth noting that this relationship will hold for anything that's called an elementary reaction. So what I'm talking about when I use the phrase elementary reaction is that the rate law matches the equation. So this means that if this is an elementary reaction, the forward reaction is first order in A, the reverse reaction is first order in B. So again, this is going to be the one point at which my stoichiometric coefficients equal my order of reactions. So that is said to be an elementary step. And one of the things that causes a reaction to be elementary is by the presence of a single transition state. Because if I have a single transition state, it means that all of those reactants have to come together to get over one net point, at which point the reaction proceeds. And we can illustrate all of these principles for the reaction of N2O with nitric oxide to form nitrogen gas and nitrogen dioxide. So in this case, we've seen this reaction before. I start with my reactants. I go over one single transition state to generate my products. And so we can generate our forward and reverse rates, again, showing that they proceed exactly as we'd expect. We have a forward reaction that is first order in both of my reactants, and we have a reverse reaction that's first order in both of the products. And we can use this to relate our rate constants to our rate reactions to our equilibrium. And again, showing that the equilibrium expression is given as the products over reactants, or the forward rate constant over the reverse rate constant. And let's go ahead and take a moment of what this looks like. So we know that our rate constant for the forward reaction is going to be a lot smaller because it is a much lower activation energy. This lower activation energy means that my reactants quickly form the products, but the products slowly form the reactants. And as a result, we tend to have a reaction that is more product favored. And so for these rates to become balanced, I need to have a lot more products than I have reactants. And it turns out this dovetails with the thermodynamics of the system. Because the products are thermodynamically favored, it means I would expect to have more products. And this again goes straight in line with what the activation energies say. So everything really comes together when we look at this in terms of elementary systems. And it's worth noting we can expand this to any elementary equilibrium, no matter the coefficients. So if I have A amount of A plus B amount of B produces C amount of C and D amount of D, and the whole system's at equilibrium, I can write my forward rate, since this is an elementary reaction, in terms of the forward rate constant, the concentration of A to however many molecules of A I need, and the same thing with B. And we can write the reverse reaction very similarly, except denoting that now C and D are my reactants, and I have a rate constant of K -1. So different rate constants, different starting materials. And then again, we can, for an equilibrium system, set these forward and reverse rates equal and solve for our equilibrium constant in terms of our rate constants or in terms of the concentrations. All of these different methods are synonymous. However, it turns out that not every reaction occurs in one single elementary step with one single transition state. And in these cases, it is worth noting the equilibrium constant still is the ratio of products over reactants, but that relationship in between the equilibrium constant and the rate constants do become a lot more complicated. So next time, we're going to dive in a little bit more detail to try and figure out how we can treat a system that has sequential reactions or has intermediates and more than one transition state. Until then, take care.